Now I take another example whereby angular momentum is only conserved relative to one point, but not to any other point. I take a ruler or a rod, and the rod had mass m and length L, and C is the center of mass of that rod, but I force it to spin about point P. And this distance is d. Think of this as a horizontal frictionless plane, and I'm rotating it with an angular velocity. Let's say we rotate it in this direction, force it about that point P. I put a pin in there perpendicular to the blackboard, and I rotate it. I'd like to know what the magnitude is of the angular momentum relative to point P. And for that, I go immediately to equation 5. So that tells me that it is the moment of inertia about that axis through point P times omega. I remember the parallel axis theorem. I know that the moment of inertia for rotation about the center of mass through this axis perpendicular to the blackboard, I know that that one equals 1/12 mL squared. Well, I just looked that up in a table because I don't remember that. So that would be the moment of inertia about this axis, and then the parallel axis theorem tells me I have to add plus md squared times omega. I'm not interested in the direction of L because that's immediately obvious. If it's rotating clockwise, then the direction of the angular momentum would be perpendicular to the blackboard and into the blackboard. I claim that at this point P, there must be a force acting on this ruler, and the force is in this direction. And I can make you see that the best way by first showing you a case of a massless rod with two equal masses at both ends. And I rotate about this axis perpendicular to the blackboard. There is going to be a centripetal force here and a centripetal force here, and the two are equal. They cancel each other out, so there will be no force on that pivot point about which the two rotate. However, if I had the situation such that this is my massless rod, and here are the two equal masses, but now I rotate them about this point, then this centripetal force is larger than this one, so now I have asymmetry, and so now there will be a force on this pin. The ruler will push on the pin, and action equals minus reaction, the pin will push on the ruler. And it is because of the same asymmetry that you have here that there will be a force from the pin on point P. However, I don't care about that force because I'm going to take the torque relative to point P. And when I take a torque relative to point P, any force through point P has no effect because the position vector is 0. But I want you to appreciate that there is a force. So if I take the torque relative to point P, I do not worry about this force. Well, the torque relative to that point P is 0, and so it's clear that angular momentum relative to point P must be conserved. Angular momentum relative to point P is conserved. Take any other point, doesn't matter which one you take. Take this point Q, take this point here, take this point here, and angular momentum is not conserved. You immediately see that if I take this point Q here, that this is the position vector, and you see that R cross F is not 0. So there is a torque relative to point Q. Angular momentum is not conserved. Only this point, that point is very special.